Hi students, in this session we will discuss about the frequency domain analysis. First of all, we will go through the sinusoidal transfer function. That means we will give a sine function as the input to a system. So the corresponding response of the system to the sinusoidal input is called a sinusoidal response. And the figure shows a diagram in which R of t is the input and C of t is the output, and the input function is a sine function, then the corresponding output C of t is called sinusoidal response. That means when we are giving input as the sine function, then the output, the corresponding output is called sinusoidal response. So the sinusoidal transfer function is the ratio of sinusoidal response to the sinusoidal input. That means here this is the transfer function t of j omega. So this transfer function t of j omega will be the ratio of output to input, that is C of t divided by R of t. So sinusoidal transfer function is the ratio of sinusoidal response to the sinusoidal input, and it is denoted by the letter t of j omega. And the sinusoidal transfer function is the frequency domain representation of the system. So we are calling the sinusoidal transfer function as the frequency domain representation of the system. So it is obtained by the ratio of sinusoidal response to the sinusoidal input. And here we are giving the input as R of t, which is equal to a sine omega t plus theta, which is a sine function. And we can represent it in the polar form as a angle theta, where a is the magnitude and theta is the angle. Similarly, the corresponding output is C of t, and which has got a magnitude and a phase, and in terms of polar form, in the polar form we can represent the output or sinusoidal response as B angle phi, and the magnitude is obtained by, see here the transfer function is t of j omega. We know from the first module that if we are given an input, then that input will be multiplied by the gain and that will give the output. So if we are giving R of t, then it will be multiplied with the t of j omega and we will get C of t. So the magnitude term in the response will be the product of the magnitude terms in the input and the transfer function. So here B is the magnitude term. So B will be equal to the magnitude of R of t, which is A into magnitude of t of j omega is modulus of t of j omega. So B equal to A into modulus of t of j omega. Similarly, angle term can be written as phi will be equal to, here the angle term is theta and here the angle term is angle t of j omega. If we are multiplying in the input with the transfer function, then the angle terms will be added. So the corresponding angle at the output phi will be equal to theta plus angle of t of j omega. So this is the frequency domain representation. Actually, the sinusoidal transfer function itself is the frequency domain representation. So we can say that a frequency domain transfer function t of j omega is a complex function of omega. So we can separate this complex function of omega into magnitude and phase functions, and these magnitude and phase functions are called frequency response. Using the frequency domain specifications, we can state this performance, we can find out the performance and characteristics of the system. So in the case of a frequency domain representation, the performance and characteristic of the system can be represented or measured in terms of frequency domain specifications. And the frequency domain specifications are resonant peak MR, resonant frequency omega R, bandwidth omega B, cutoff rate, gain margin kg, and phase margin gamma. These are the frequency domain specification. It is used to measure the performance and characteristic of the system in frequency domain. So these quantities are very important. So the frequency domain specifications are resonant peak MR, resonant frequency omega R, bandwidth omega B, and cutoff rate, gain margin kg, phase margin gamma. Let us see each one separately. First one, what is resonant peak? So resonant peak is the maximum value of closed loop transfer function. And what is resonant frequency? and the frequency at which the resonant peak occurs is called a resonant frequency. And next is the bandwidth. It is a range of frequencies for which the system normalized gain is more than minus 3 dB. And the frequency at which the gain is minus 3 dB is called a cutoff frequency. So the bandwidth is, we can say that bandwidth is a measure of the ability of the feedback system to reproduce the input signal. So a large bandwidth corresponds to a small rise time and fast response. Next is cutoff rate. See, there is one more term, the frequency at which the gain is minus 3 dB is called a cutoff frequency, and cutoff rate is the slope of the log magnitude curve near the cutoff frequency is called a cutoff rate. Next is gain margin. Gain margin can be defined as the value of the gain that is to be added to the system in order to bring the system to the verge of instability. That means the gain margin it is expressed in dB and it is given by the negative of the dB magnitude of transfer function g of j omega, and the gain margin indicates the additional gain that can be provided to the system without affecting the stability of the system. That means it is the additional amount of the gain that is given to the system without affecting the stability of the system. And we will have an equation for the gain margin kg equal to 1 divided by modulus of g of j omega at Pc. Pc means phase crossover frequency. That means gain margin kg can be defined as the reciprocal of the magnitude of the open loop transfer function at phase crossover frequency, that is omega Pc, that is the phase crossover frequency. And if we can define the phase crossover frequency is the frequency at which the phase of the open loop transfer function is 180 degree, and that frequency is called phase crossover frequency. That means in the case of phase crossover frequency, the phase of the open loop transfer function will be 180 degree. So gain margin is obtained by this equation, and in the dB value of the gain margin can be obtained by kg in dB equal to 20 log kg. So we get an equation 20 log 1 by modulus of g of j omega at phase crossover frequency. So modulus of g of j omega Pc is the magnitude of the g of j omega at omega equal to omega Pc. And then frequency at which the phase of the open loop transfer function is 180 degree is called phase crossover frequency. Next frequency domain specification is phase margin, which is denoted by the letter gamma, and actually it is the additional phase lag that is to be added at the gain crossover frequency in order to bring the system to the verge of instability. So the gain crossover frequency, which is denoted by the omega gc, is the frequency at which the magnitude of the open loop transfer function is unity. Actually, the phase crossover frequency is the frequency at which the phase of the open loop transfer function is 180 degree, and the gain crossover frequency omega gc is the frequency at which the magnitude of the open loop transfer function is unity. So phase margin gamma is obtained by the equation gamma is equal to 180 degree plus phi gc, where phi gc is the angle of g of j omega gc, and angle of g of j omega gc is the phase angle of g of j omega at omega equal to omega gc. So these are the frequency domain specification. Next we will find the frequency domain specification of the second order system. So we will find each frequency domain specification separately. First we will find find the frequency domain specification for the second order system, and first we will consider the resonant peak MR. What is resonant peak MR? Resonant peak is the maximum value of the magnitude of the closed loop transfer function. So first we will take, for getting the equation for resonant peak MR, we will take the second order system and whose transfer function is given by C of s by R of s is equal to m of s, that is equal to omega n square divided by s square plus 2 epsilon omega ns plus omega n square. This is the basic equation for the second order system. This is the transfer function of the second order system. And if you are applying a sinusoidal transfer function m of j omega, that is obtained by putting s is equal to j omega. So if we are substituting s is equal to j omega in the above equation, we will get a omega n square by j omega square into 2 epsilon omega n j omega plus omega n square. and we will get it as omega n square divided by minus omega square plus 2j into epsilon into omega n into omega plus omega n square. In this term we will take omega n square outside so that we will get the equation like this. So these all are simple mathematical procedures. So in this case this is the equation. See here omega by omega n is common, so we can substitute it as omega by omega n is equal to u, which is a normalized frequency. So m of j omega will get the form 1 divided by 1 minus u square plus 2 j into epsilon into u, where m is the magnitude of the closed loop transfer function and alpha is the, we are substituting, we are assuming that we have a function m of j omega. In this case its magnitude is denoted by the letter m and its angle is denoted by the letter alpha. So our magnitude will be obtained by magnitude of m of j omega, which will be obtained by the equation square root of real part square plus imaginary part square. So we'll get the equation like this. And in order to find the angle, we have an equation angle will be equal to, if a plus ib be the form, then angle will be equal to tan inverse b by a. So we will get the angle of m of j omega as imaginary part is 2 epsilon u divided by real part is 1 minus u square, and here angle alpha will be equal to minus of tan inverse 2 epsilon u divided by 1 minus u square. So next we will find the, we have the magnitude term and the angle term, and now see we can find the resonant peak. We know that a resonant peak is the maximum value. So finding the resonant peak, we know the condition for finding the maximum value. In order to find the maximum value, we will take the first derivative and we will equate the first derivative to 0. And we have a substitution here. We can substitute ur equal to omega r by omega n, which is normalized resonant frequency, and we have an equation 4.9 that gives the value of m. And if we are taking the first derivative of that equation m, that is dm by du, that means d by du of 1 minus u square all square plus 2 for epsilon square into u square all raised to minus 1 by 2. This is the equation. And in this equation, if we are taking the first derivative, we will get a different terms. So this is simple derivative equation, and finally we got the equation like this: 4u into minus 1 minus u square into minus 8 epsilon square into u divided by 2 into 1 minus u square all square into 4 epsilon square into u square all raised to 3 by 2. So we have to put the condition for maximum value, which that means first derivative will be equal to 0. So we can equate it to 0. So when we are equating it to 0, that means the numerator will be equal to this term will be multiplied with this. So we will get the equation 4ur into 1 minus ur square minus 8 epsilon square into ur equal to 0. And in this case we can rearrange the equation. So we will get the value of ur square equal to 1 minus 2 epsilon square, and here ur will be equal to square root 1 minus 2 epsilon square. Therefore we will get the value of ur as square root 1 minus 2 epsilon square. Therefore the resonant peak occurs at ur equal to square root 1 minus 2 epsilon square. So this is the point where resonant peak occurs. So we can substitute the value of ur in the equation for mr. So here we have an equation for m. So here we have an equation for m. So we can substitute for u as ur. So we will 4 into ur into 1 minus ur square minus 8 epsilon square into ur. See, sorry, this is a slide. So mr equal to 1 minus instead of u we can substitute ur. So we will get the equation like this: 1 minus ur all square plus 4 epsilon square into ur square into raised to 1 by 2. And here we can multiply the, we can expand the terms and we can cancel the similar terms. So we will finally get an equation like 1 divided by 4 epsilon square minus 4 epsilon raised to 4. In this case epsilon square, 4 epsilon square can be taken outside. Finally we get the value of mr as 1 divided by 2 epsilon into square root 1 minus epsilon square. So this is the equation for the resonant peak mr. So resonant peak mr is equal to 1 divided by 2 epsilon into square root 1 minus epsilon square. So this is the equation for resonant peak. So we have find out the first time domain specification. So that's all about this topic. Thank you.